a circle of towering stones, whispering of ancient societies and arcane rites. Known as Stonehenge, this imposing monument has dominated the imagination of archaeologists and visitors for centuries.
What if everything you've been taught about our ancestors is wrong? What if the people who built Stonehenge weren't primitive farmers, but master engineers who understood principles we're only now rediscovering? For 4,500 years, those massive stones have stood perfectly aligned, interlocked, and engineered to survive forces that would topple modern buildings.
Thousands of years ago, at the dawn of civilization, Stonehenge represents a crowning achievement for our ancient ancestors. But why did they build it here? Why choose this place?
No concrete, no steel, no modern tools, just stone. And a level of precision that should be impossible for a society supposedly living in the Neolithic. Today, we're uncovering the truth they never taught you in school, and it will change everything you think you know about human history. 4,500 years of perfect precision. Start with the basics, but even the basics at Stonehenge are extraordinary. The monument sits on Salisbury Plain in Wiltshire, England, at about 8 miles north of Salisbury. It consists of two main stone types, massive sarsen stones forming the outer circle and inner horseshoe of trilithons, and smaller blue stones arranged in various configurations within the sarsen structures.
In the 19th century said there was a blue stone from it, and you only get blue stones at two places, the Preseli Mountains in Wales and the big collection of rocks down the road at Stonehenge. So it's a really, if this did have a blue stone in, that makes it incredibly important.
The sarsen circle originally comprised 30 upright stones, each approximately 13 feet tall and weighing around 25 tons, capped by 30 lintel stones creating a continuous ring 13 feet above ground. Inside this circle stand 5 massive trilithons, pairs of uprights supporting lintels arranged in a horseshoe pattern, with the largest trilithon at the closed end standing over 24 feet tall with estimated stone weights exceeding 40 tons. Now here's where it gets interesting. Those blue stones, weighing 2 to 4 tons each, came from the Preseli Hills in Wales, approximately 140 miles away. And the sarsens came from Marlborough Downs, roughly 20 miles north of the site. The conventional dating place's main construction around 2500 BCE during the late Neolithic period, though the site shows evidence of earlier activity. But dates and distances don't capture what's truly remarkable here. What immediately strikes structural engineers when they examine Stonehenge, what makes them shake their heads in disbelief, is the precision of the joinery. The lintel stones aren't simply placed atop the uprights like a child stacking blocks. They're locked in place through mortise and tenon joints, the same sophisticated joinery system used in modern timber frame construction and traditional woodworking. The top of each upright stone has a protruding knob called a tenon carved into it with extraordinary precision. The underside of each lintel has corresponding holes, mortises, carved to receive those tenons with tolerances that would impress a modern machinist. When the lintel is placed, the tenons fit into the mortises, preventing the lintel from sliding off even under extreme lateral forces. But it gets better. The lintels are connected to each other through tongue and groove joints on their sides, creating a continuous ring where each lintel locks to its neighbors. This three-dimensional interlocking system, vertical locking through mortise and tenon and horizontal locking through tongue and groove, creates a structure where forces are distributed across multiple stones rather than concentrated at single points. This is sophisticated structural engineering, not primitive construction. Now here's where your brain should start asking uncomfortable questions. Creating these joints in massive sarsen stones using Neolithic stone tools is extraordinarily difficult, bordering on impossible with the technology we believe they possessed. Sarsen is a form of silicified sandstone with Mohs hardness around 6 to 7, hard enough that bronze tools cannot effectively cut it, and even stone tools require enormous effort to shape. Recent analysis of tool marks on Sarsen surfaces shows evidence of pecking, repeatedly striking the stone with harder stone hammers to gradually abrade away material. Creating the flat surfaces of the stones would require thousands of hours of sustained pecking per stone. Creating the precise three-dimensional forms of the tenons and mortises would require even more careful work, removing material gradually while constantly checking dimensions and fit. Think about what that means practically. How did Neolithic builders achieve the precision required when the tenons must be sized correctly to fit the mortises within incredibly tight tolerances? Too large, and the lintel won't seat. Too small, and the joint is loose, and the structure fails. The mortise holes must be positioned correctly on the lintel so they align with the tenons when the lintel is placed. Given that lintels weigh several tons and are positioned 13 feet in the air, test fitting through trial and error would be extremely difficult, not to mention catastrophically dangerous. This suggests something that challenges our entire understanding of Neolithic capabilities. If the builders had measuring and planning systems sophisticated enough to ensure joints would fit before the stones were erected. They were working to predetermined dimensions, checking their work against standards, and achieving tolerances that required systematic quality control. This isn't primitive construction where you hammer away and hope for the best. This is precision engineering with quality assurance protocols that rival modern construction standards. Let that sink in. People supposedly without writing, without formal education, without any of the tools we consider essential for engineering, were implementing quality control systems that ensured precision fits on components weighing tons, positioned stories above ground, where failure meant death and wasted years of labor. A Stonehenge beyond history. The foundation design shows similar sophistication that becomes more impressive the deeper you dig into it. Ground-penetrating radar surveys conducted in recent years have revealed that the Sarsen stones aren't simply placed in holes dug into the ground. They sit on carefully prepared foundations that demonstrate an understanding of soil mechanics and load distribution that supposedly doesn't develop until classical antiquity. Each upright stone has a pit dug to approximately 1/3 of its length, which any modern structural engineer will tell you is the correct proportion for stability. The bottom of the pit contains packing material, smaller stones, and chalk rubble that distributes the weight of the upright stone across a broader base, reducing pressure per square inch on the underlying soil and minimizing subsidence risk. The stones were then tilted into their pits, probably using timber scaffolding and ropes, and held upright while the pits were backfilled with more packing material that was rammed tight around the stone base. This creates a foundation that grips the stone, prevents tilting, and distributes loads to minimize settling. Modern foundation engineering uses these exact same principles. Large structures need foundations that distribute loads across sufficient area to prevent excessive soil pressure that causes settling. The Stonehenge builders, whether intuitively or through inherited knowledge, applied these principles 4,500 years ago. But here's what should make your jaw drop. The foundation pits aren't of uniform depth. Ground-penetrating radar shows variation in pit depths, corresponding precisely to variations in stone heights and weights. Heavier stones have deeper pits with more packing material. Lighter stones have shallower pits. This suggests the builders understood that different stones required different foundation approaches based on their specific load characteristics. They were adapting their technique based on engineering calculations, not following a one-size-fits-all approach. This is sophisticated engineering thinking, analyzing each stone's specific requirements and designing foundations accordingly. It requires understanding the relationship between weight, foundation depth, soil-bearing capacity, and long-term stability. And so here's the question that establishment archaeology can't answer. How did Neolithic people develop this understanding without formal engineering education, without written technical knowledge, without the accumulated wisdom of previous civilizations that we can document? The silence on this question is deafening. The stone selection itself reveals sophisticated material knowledge that challenges everything we think we know about Neolithic technological capabilities. Sarsen stones are naturally occurring, but not all sarsen is equal, and the stones used at Stonehenge show remarkably consistent characteristics that indicate careful selection based on engineering properties. They're dense, fine-grained, and relatively free of major flaws that would create weak points prone to fracturing under stress or weathering. A recent geological analysis comparing Stonehenge sarsens to stones still present at Marlborough Downs quarries shows conclusively that the builders were selective. They didn't use just any available stone. They chose stones with optimal properties for durability and workability, properties that required understanding material science at a level we don't attribute to Neolithic cultures. This implies they could assess stone quality through testing or observation, distinguish between superior and inferior material based on characteristics that affect long-term performance, and were willing to invest enormous additional effort in transporting better stones from farther away rather than using closer but inferior material. That's not survival mode thinking. That's long-term engineering planning that prioritizes quality over convenience. The shaping of the stones demonstrates additional sophistication that becomes apparent when you look closely at what appears at first glance to be simple rectangular blocks. The sarsen uprights aren't simple rectangular forms. They're shaped with slight curves and tapers that serve both aesthetic and structural purposes. The stones are wider at the base and narrower toward the top, creating a gentle taper. The surfaces facing inward toward the monument center are flatter and smoother than the outward-facing surfaces, creating a refined interior space. The lintels are shaped with a slight curve on their inner face, so they form a true circle when assembled rather than a polygon. This shaping serves multiple functions simultaneously. The taper makes the stones appear taller and more dramatic from inside the monument, creating a psychological impact on observers. The inward-facing smoothness creates a more refined and intentional interior space. The curved lintels ensure a true circular form that has symbolic and practical implications. But here's what matters from an engineering perspective. The shaping also affects structural performance in ways that extend the monument's lifespan. The taper concentrates mass at the base, where stability is most critical, lowering the center of gravity. The smoothing of surfaces reduces stress concentrations that could lead to cracking under thermal cycling. The curved lintels distribute forces more evenly around the circle, rather than concentrating stress at corners where polygonal segments meet. Whether these effects were intentionally designed for structural benefit or were fortunate consequences of aesthetic choices, the result is a structure optimized for longevity in ways that modern structural analysis confirms are genuinely effective. Neolithic genius. The arrangement of the stones at Stonehenge reveals a geometric sophistication that far exceeds what we typically associate with Neolithic cultures. The sarsen circle measures approximately 33 meters in diameter, and the spacing between the uprights is remarkably consistent, averaging around 1.1 meters from center to center, with variation measured in mere centimeters. Achieving this level of consistency requires careful surveying, precise measurement systems, and coordination across teams to ensure each stone is positioned according to a predetermined plan. It demands foresight, organizational skill, and an understanding of geometry that is astounding for a society without written records. Within the sarsen circle, the trilithons are arranged in a horseshoe, with the open end facing northeast, toward the sunrise on the summer solstice. The largest trilithon at the closed end aligns precisely with the monument's central axis. This axial organization demonstrates deliberate planning. The structure is organized around sight lines and astronomical alignments established through long-term observation and meticulous record-keeping. It is not random placement. It is a coordinated blueprint designed to integrate celestial phenomena into the very architecture of the monument. Even the horizontal lintels reflect sophisticated design thinking. They are not perfectly level relative to true horizontal. Instead, they are aligned relative to the average ground slope, creating the appearance of levelness for observers standing inside the monument. This subtle prioritization of human perception over abstract geometric perfection indicates an advanced understanding of visual psychology, centuries before such principles were codified in classical Greek architecture. The builders were thinking not just structurally, but experientially, designing a space to communicate meaning, awe, and symmetry as humans perceive it. Astronomical alignments further reveal extraordinary observational knowledge. The monument's axis aligns with sunrise on the summer solstice and sunset on the winter solstice. Recent studies also suggest alignments with lunar events, including the 18.6-year cycle of maximum and minimum moonrise and moonset positions. When accurately tracking these cycles requires decades of sustained observation, careful record-keeping, and a deep understanding of celestial patterns. Without written language, such knowledge had to be transmitted orally, preserved across generations with remarkable fidelity, a level of cultural continuity and institutional knowledge that challenges conventional assumptions about Neolithic society. Stonehenge's construction sequence deepens the mystery. The site was built over approximately 1,500 years, evolving through multiple phases. Around 3000 BCE, the circular earthwork ditch and bank were established. Bluestones were erected around 2900 BCE, then rearranged multiple times over subsequent centuries. The sarsen stones, which dominate the monument today, were erected around 2500 BCE. This extended timeline implies multi-generational planning and sustained technical expertise. Maintaining precise design intentions, construction methods, and astronomical alignments over centuries without written records is extraordinary. Oral tradition alone seems insufficient to explain such precision. Some system of knowledge preservation and transfer must have existed. The labor organization required to execute the construction is staggering. Moving a 25-ton sarsen stone 20 miles using only rope, wooden rollers, and human muscle likely required hundreds of workers coordinating in unison. Erecting uprights demanded timber scaffolding, controlled tilting, and careful pit backfilling. Raising the 13-foot lintels involved rolling them up earthen ramps and aligning mortise and tenon joints with near-perfect precision. Missteps could be fatal. A falling multi-ton stone would instantly kill anyone beneath it. The risk management, planning, and engineering judgment necessary for success rivals modern construction practices. What is particularly confounding is how the builders acquired such competence. Trial and error learning seems implausible. Catastrophic mistakes would destroy months or years of labor and result in significant loss of life. This implies prior experience with similar projects, inheritance of advanced construction knowledge from earlier, now lost traditions, or some theoretical understanding of physics and mechanics, none of which fit comfortably within conventional narratives of Neolithic technological development. Stonehenge was not the product of improvisation. Every detail, from the spacing of uprights and interlocking joinery, and to the selection of durable sarsen stones, to the integration of astronomical alignments, reflects deliberate engineering, careful observation, and long-term planning. The monument embodies principles of structural mechanics, material science, load distribution, and risk management, all applied without written language, steel, or mechanical advantage. It demonstrates an extraordinary level of cultural and cognitive sophistication. Ultimately, Stonehenge challenges the conventional portrayal of Neolithic societies as small, isolated communities with rudimentary tools and limited social organization. Its construction required sustained vision, institutional knowledge, and multi-generational collaboration. The monument's survival is proof that the builders understood structural stability, human perception, and celestial cycles in ways we are only beginning to fully appreciate. Stonehenge is not simply a prehistoric monument. It is a testament to human ingenuity, cultural continuity, and engineering mastery, inviting us to reconsider what our ancestors were capable of achieving, and how much of that knowledge has been lost or hidden through the passage of time. The secret architects. Stonehenge has survived 4,500 years of storms, frost, and seismic events, a feat that few modern structures could match. While many of its stones have toppled over time, especially during the Roman and medieval periods when the monument was neglected, the remaining uprights reveal engineering sophistication far beyond what conventional narratives attribute to Neolithic societies. Modern structural analysis shows that the design incorporates redundancy, and a principle where structures can lose individual elements without catastrophic failure. If one upright fails, the lintels it supports may collapse, but the surrounding stones remain stable, distributing loads through the interlocking system. This graceful degradation, a hallmark of sound engineering, ensures resilience over centuries, an approach taught in contemporary engineering schools, yet applied here millennia ago. The selection of materials further illustrates deliberate planning for longevity. The builders chose sarsen for its extraordinary durability, resisting weathering far better than limestone or chalk. Sarsen's resistance to thermal stress and freeze-thaw cycles meant that structural integrity could endure over millennia. Blue stones, though smaller and geologically diverse,
The inner blue stones are from Wales, and we now know that the central altar stone is from northeastern Scotland.
were arranged to provide stability through mutual support, demonstrating an understanding of how materials of varying properties could work together structurally. This wasn't happenstance, it was deliberate design optimized for survival. The joinery system is another striking testament to advanced knowledge. Mortise and tenon joints and tongue and groove connections lock stones together, preventing displacement even under extreme dynamic loads. During the Great Storm of 1703,
it ranks alongside the Great Fire of London and the Great Plague, but hardly anyone has ever heard of the Great Storm of 1703.
when hurricane-force winds destroyed buildings across southern England, Stonehenge remained intact. The interlocked structure absorbed and distributed forces, preventing individual stones from being toppled, a principle modern architects recognize as fundamental to earthquake-resistant and load-distributing design. Foundations contribute equally to Stonehenge's endurance. Despite 4,500 years of soil movement, settlement, and erosion, most uprights remain essentially vertical. Ground-penetrating radar reveals minimal subsidence, showing that the chalk rubble packing beneath the stones effectively distributes loads. Unlike modern structures, which are designed for service lives of 50 to 100 years and require frequent maintenance, Stonehenge's engineering has endured with minimal intervention over nearly 5 millennia. This longevity raises a critical question. Was Stonehenge's survival the product of fortunate material choices and construction practices, or the result of deliberate engineering? The evidence strongly supports deliberate design. The joinery system, foundations, and material selection serve no practical purpose if the goal was merely to erect stones quickly. They make sense only if the builders anticipated the structure enduring not just for decades, but for millennia. The monument's creators clearly planned for a future they would never see, constructing a legacy meant to outlast their culture, their society, and the generations that followed. The organizational demands of Stonehenge are equally staggering. Neolithic Britain is often portrayed as a collection of small farming communities with limited hierarchy, no writing, and no formal institutions. Yet the construction of Stonehenge over 1,500 years required sustained technical knowledge, social coordination, and cultural continuity. Such long-term projects imply not just advanced engineering.
I mean, it's such an amazing monument, but what we tend to miss are the people who built it. So what bringing all these objects together will let us do is let us see the people who built Stonehenge and let us understand their relationship.
But institutions capable of maintaining knowledge and organizing labor across generations, a level of sophistication rarely credited to prehistoric Europe. Some researchers suggest that Stonehenge was part of a broader network of Neolithic societies spanning Atlantic Europe, from Iberia to Scandinavia. These interconnected communities shared astronomical knowledge, engineering techniques, and trade networks, demonstrating that technical and cultural sophistication was not isolated, but widespread. If true, Stonehenge represents a pinnacle of a continental civilization's collective knowledge rather than an isolated achievement, raising uncomfortable questions about the origins and transmission of that expertise. Conventional models of cultural development, from primitive to complex, struggle to account for these realities. The alternative hypothesis that knowledge was inherited from earlier, now lost cultures lacks direct evidence but aligns with observable patterns. Stonehenge's survival, its joinery, its foundations, and material choices all point to deliberate engineering. Its astronomical alignments are accurate, verified by modern calculations. Its foundations, material selection, and interlocking design are practical solutions to forces that remain relevant today. These weren't accidental innovations. They required understanding of mechanics, geometry, and material science beyond what traditional accounts attribute to Neolithic societies. Stonehenge stands as proof that our ancestors were capable of far more than history textbooks suggest. Its survival is the ultimate test of engineering. Structures don't last millennia by chance. And they endure because builders anticipated stress, planned redundancy, selected optimal materials, and designed foundations to last generations. Whether this knowledge was accumulated through experience, inherited from earlier unknown civilizations, or developed through sophisticated theoretical understanding, the result is clear. Stonehenge was engineered for permanence, longevity, and stability. The monument challenges fundamental assumptions about prehistoric human capability. It forces us to reconsider the technological, organizational, and cultural sophistication of societies traditionally portrayed as simple or primitive. Every joint, every carefully chosen sarsen, every interlocked stone speaks to a deliberate, thoughtful application of engineering principles that modern analysis continues to confirm. Stonehenge is not merely a pile of rocks. It is a 4,500-year-old testament to knowledge, planning, and execution that far surpasses the conventional understanding of its builders. Its survival demands recognition of Neolithic engineering brilliance and invites us to ask deeper questions about the origins of human technological achievement. Stonehenge has stood for 4,500 years, defying time, weather, and our assumptions about human capability. Its stones don't just tell a story, they demand a question. Who truly understood this knowledge, and how did it survive before us? If Neolithic societies were capable of this, what else have we overlooked? The evidence is there, waiting for those willing to look, and the deeper you dig, the more the past refuses to fit the story we've been told.